I talked about phosphoric acid already. I said the big thing about any polyprotic acid, it dissociates in a series of steps. If we talk about not the ethylene diamine, the ethylene diamine tetraacetic acid, there we are. That's a tetraprotic acid. EDTA, we talked about it as a complexing reagent. It's a tetraprotic acid. It means it has 4 equivalent points. Might be a little bit hard to distinguish them and involve more complicated calculations that we want to do, because if you have 4 equivalence points and you're working between pH 1 and pH 13 or so, that means that the Ks are almost all the same. You have to do a bunch of simultaneous equations. So we're sticking with things like phosphoric acid, where the Ks differ by a lot. We're not going to do anything with phosphoric acid except to look at something. But what's the polyprotic acid that you've been using for a while? Somebody said H2S, I heard that. That's Ka1, that's the first step. And that's Ka2. And looking into your book, and by the way, most books give you about the same number for Ka1. I don't necessarily pick this book because it only gives you one significant figure, so I go to a different book. But I'm just going through to get Ka1. There it is. He gives you 1 times 10 to the minus 7. Other books will give you slightly smaller, larger numbers, because there's a lot of not confusion, but a lot of difference in the way you want to define this. I'm going to use your book value right now. On the quiz, I might change that. That's why I say don't memorize the Ks, because when I want to give you different versions of the quiz, what do? I just give you the same problem with a different K. I can do that, because all I'm seeing is whether you can do the calculation. If you really had to do it in the real world, you go out and look it up. And by the way, for this one, you would find some different, considerably different numbers for Ka2. This book gives you 1 times 10 to the minus 19. And notice he only quoted one figure, because some books are going to give you numbers like 10 to the minus 21, all the way down to 10 to the minus 17. So it depends on which book you're using, so you just use the information the author gave you, because that's the way he wants you to do the calculations. And the reason you have some trouble here is as you start making it more acidic, it's harder to define what the concentrations of these species are when you're trying to make the measurements. So people just get around that problem and say, well, I'm not doing a big treatise on hydrosulfuric acid. If I were, I'd be much more careful with my definitions and things. And somewhere there is a consistency in the tables, but a lot of the textbooks use whatever number they learned when they grew up. So you're stuck with that. Now, one of the things we can do out of this is look at principal species. I already told you, when you do procedure 5C, where you're precipitating things out, this is the principal species. And I said I'd prove that to you later, but it's obvious if you have some hydrogen ion and you're adding HCl, you're shifting the equilibrium in this direction, common ion effect. So you would expect this to be the principal species. What I haven't told you yet, when I started talking about procedure 15, this is going to be the principal species. And you say, how can you prove that? And I said, simple. I'll start up here. Just minus. Now, one of the assumptions, and This is what causes problems, by the way, when they're trying to determine all these other K's in here. When you have a saturated solution of H2S, it's about a 0.1 molar solution. Okay, when you decompose your thiosediment, you're making a saturated solution of H2S. It's about 0.1. It changes with temperature, and it also changes with the pH. But not enough to worry about. Not enough for us to worry about. Let's put it like that. So what I'm going to do is look at this ratio right here. So I'm going to take and it's going to be equal to and suppose I have a neutral solution. Suppose I set it up with my acetic acid, HCl, so I have a buffer, and it's going to be close to 7. I can't make it exactly 7. But just for the heck of it, since this is, the pH is 1 times 10 to the minus 7. What does that say about these two numbers? They're the same. So anything less than pH 7, if I have concentration of hydrogen ion 10 to the minus 6, it says that the concentration of H2S is 0.1 times, I'm sorry, the concentration of HS minus, you can't see my minus, and I always complain about that when we do that, was this concentration right here is 0.1 times this. This means that this is 10 times bigger than this. So as soon as you're below pH 6, and certainly working with 2 molar HCl, you're well below pH 6, it means this is the principal species. Because this number gets smaller, this number gets bigger because this ratio gets smaller. So below pH 7 roughly, at pH 7 they're about equal, but we don't do anything at pH 7. We're working acidic solution. So this number becomes bigger than this because this decimal number gets smaller. What happens if we go above pH 7? Now we can look at it, let's say pH 8. Okay, that makes it what? 10. It now says this number is 10 times bigger than this number. So HS minus becomes the principal species once you go above pH 7. When we're doing procedure 15, we're working in a buffer of what? You add ammonium chloride, you add ammonia. It makes a buffer solution, pH greater than 7. So this becomes the principal species. And you may remember I said the only way you can have sulfide ion as the principal species if you have a pH greater than what? 19. You don't have to remember that, but how did I get that? Well, now I look at Ka2. This one right here. So if pH is, this is 1 times 10 to the minus 19th, I'm going to rearrange this. Ka2 over concentration of H3O plus equals HS minus. So if this is 1 times 10 to the minus 19th, Ka, so when I start doing that to look at this, if this is 10 to the minus 19th, these two things are equal in concentration. So it has to be smaller than 10 to the minus 19th down here for the hydrogen ion to have more sulfide than HS minus. So you'll never have the S2 minus ion as the principal species. Okay? Like I said, when I tell you to write the net ionic equations, I'll tell you what to put in there, and then eventually I'll justify it. So at the beginning of procedure 5, I said we're using H2S as the principal species. Because as long as we're below pH 7, that is the principal species. Once you exceed pH 7, the HS minus becomes the principal species. And if I put 10 to the minus 7th in here, 10 to the minus 8 for the hydrogen, pH 8, this would make this ratio 10 to the minus 11. That means this is still 10 to the 11th times smaller than this. So the H2S is HS minus the principal species. And we basically can't make it basic enough for this to be the principal species. So when your book writes something like this, I said this can't be a net ionic equation because the definition of the net ionic equation says you put in principal species. If you have a lot of copper ion, you can put in 0.1 molar, 0.01 molar, depending on how you compare it to known. And this is never going to be the principal species. You're working an acidic solution in procedure 5, so you'd have to use H2S. Now when we get to procedure 15, there we're working with a basic buffer. Then you're going to use HS minus because you'll be above pH 8. You'll be up around pH 9 or 10. We could probably calculate the pH of that buffer solution. That'll save it for the quizzers. Okay. So that takes care of one thing.